Welcome back from the lunch break. Now we're going to learn how we can build a fusion reactor and become familiar with the tools. Thank you, Jonathan, for joining us.
Thanks a lot for having me. So what this is all about is stellarator design, so building fusion reactors like this one over here. And I had the honor a couple of weeks ago on the 16th of April to welcome a certain person in our lab that I built up and run at Proxima Fusion. And I'm going to let them tell you what this is all about. So here we go.
So talking about fusion energy, let's start with fission, which is nuclear reactors. Where you take a big atom like uranium and you break it in pieces, great energy. Fusion is different. You take a small one and you fuse it. So here comes the problem. Normally these atoms, they don't want to fuse. They have a repelling electrolytic reaction. First thing is what you want to do, you take a small atom like hydrogen, actually it's deuterium but it's hydrogen, which is a gas, which has a proton and an electron. First we want to strip off the electron. How do you do that? You heat it up to 15 million degrees in the sun, that's where it happens in the sun. Here on Earth we need 150 million degrees, so 10 times hotter than the sun. Then the electron goes away, and then you have a kind of a gas which is called plasma. It's electrons and protons moving around. Now you have a gas which conducts. When it conducts, you can use magnets to accelerate it. Why do you want to do that? Because in order to come across this repelling reaction, you need to bump them into each other. So accelerate them, create a chaotic bumper chamber, and let these atoms, these protons, bump against each other and eventually fuse in great energy. And now I show you how this chaotic bumper area would look like. A bumper area for plasma contained in big magnets.
All right, here we go. And after this, you already know everything. And we just do a little bit of a further deep dive in this talk, obviously. The big thing that we want to do is we want to build a fusion reactor because fusion is the ultimate source of clean energy. It's a process that powers the stars by forcing light nuclei, so the cores of atoms together. Their mass difference from the resulting products is converted according to E equals mc squared, a formula that some of you might know, into energy. The thing is though that the sun, which we know as the closest star, is remarkably inefficient at doing that, and it needs its gravitational forces to keep the particles together so that eventually after billions of years they fuse. And what we want to do here on Earth is that we use this process to generate a clean, safe and effectively limitless energy source by using a slightly different process than the sun though. And I would boldly claim that when we enter the fusion era, we will end energy scarcity on Earth, which in particular in the age of AI is a big topic. A little bit about me. I'm co-founder and head of labs at Proxima Fusion. I have a PhD in plasma physics from the Max Planck Institute for Plasma Physics in Greifswald in the very northeast corner of Germany, where I did modeling, numerical modeling, physics analysis for the so-called Wendelstein 7X stellarator experiment. And my open source interests span between mostly numerics, physics, a little bit of reverse engineering. So here you see my private GitHub repo. Feel free to check that out. And a couple of contributions to the open source community is like a tutorial for the FFTW, fast Fourier transform library, some infrared camera image reading, reverse engineering, which I did together with my brother Benny. Then we have some 15-digit accurate magnetic field computations, which was published in 23. And there's also an open source library now. I did recently a reverse engineering of the original Macintosh 68K ROM for a little bit of a historic computing project. And something that I will cover in this talk is that I cleaned up and rewrote the Variational Moments Equilibrium Code, which is a numerical tool that is used to model these kind of stellarators that we looked at. And VMEC++ is open source and also 200 pages of LaTeX documentation, which you can find on arXiv that I wrote in the context. Now also in docling in the original repo, so that we can use it for AI-assisted improvements on the code base itself. And I also like a little bit of hands-on engineering, so I did some high voltage experiments in my younger times. For example, he built a 25 kilovolt high voltage transformer that can make some arcs, and also some machine tools reconditioning. So this is an old milling machine which I acquired during COVID and then overhauled. And this gentleman here in the center is Thomas Klinger, who's the head of the Wendelstein 7X project during its construction time, and we spent a lot of time where he explained to me what went wrong, what we would do better in the upcoming fusion experiments now after Wendelstein 7X. And essentially everything that I know about fusion, I know from him, and this is why I'm very grateful about this. I'm going to talk about three things in this talk. One is Proxima Fusion in general. What is even the roadmap? What do we want to do? What's our approach? The second thing is that I'm going to give a little bit of background on this VMEC++ tool. What was difficult in building it? How is it structured? What are use cases? How can you get access to it and contribute to it? And the third one is a little bit something about the ConStellaration challenge, which is a AI machine learning challenge that we posed together with Hugging Face last year. This is one of the most openly available large-scale applications of this VMEC tool then in the context of Fusion. Proxima Fusion aims to build a stellarator, and it does that not a tokamak like ITER, this big machine in southern France, because design and not control holds the key to fusion. What do we mean by that? If you look at the tokamak, it looks like a very much simpler design, and it creates the magnetic field that you need in this machine to contain the plasma with a current that runs through this plasma. And this is simple to design because it's axisymmetric, but it's very hard to operate. Stellarators, on the other hand, if you look at this looks like a completely different beast, obviously, in terms of the engineering complexity. And this is because this twisted magnetic field, which looks a little bit like a Möbius strip, is generated by numerically optimized coils, like these silvery arm rings that you can see here around. And they are harder to design, but in the end, the machine becomes simpler to operate. So this is what we chose for Proxima, because we want to get eventually to a steady state, continuously 24/7 running power plant. And for that, we consider this to be the better approach. How do we get there to a commercial fusion power plant with this approach? We start from the well-known Wendelstein line of stellarators that have been built in the last 60 years in the context of the Max Planck Institute for Plasma Physics in Garching and eventually later in Greifswald for Wendelstein 7X. And we want to get to Stellaris, our first proposed fusion power plant concept. And as an intermediate step, we introduce a machine which we call Alpha, which is supposed to deliver the first smallest step basically on the path towards the fusion power plant, which is that from this plasma ring, which is where the actual fusion reactions happen, you want to get more energy in terms of neutrons out than you have to put in terms of microwave heating power. This is like if you cannot even do that, then there's no hope to ever build a power plant which actually delivers power to the grid or eventually also makes you money. How do we get there exactly? So we have Wendelstein 7X, this machine in Greifswald, and we want to get to the fusion power plant. And something that we can directly carry over from W7X is steady state operation. Because W7X is a fully superconducting machine. That means all these magnet coils, in this case here orange and red, are cooled down to minus 269 degrees Celsius, roughly 4 Kelvin. It's the temperature of liquid helium. And at these temperatures, if you build the coils out of certain materials, in this case it's called niobe titanium, this becomes superconducting, so you don't have losses, electrical losses, when you generate these big magnetic fields, which is a game changer for creating these strong magnetic fields that we need to contain this hot fusion plasma. And Wendelstein 7X has shown already how to do this and also how to eventually operate this machine for 30 minutes steady state, at which point also thermal equilibration effects come into play. And so you really need to properly design this machine for that. And W7X is the first machine where this was rigorously carried through. And in between we have Alpha. This builds on top of Wendelstein 7X. It's roughly the same size. So this is 16 meter end-to-end. Wendelstein 7X weighs roughly 700 tons. And Alpha is probably going to be weighing 2,000 tons, although also only 16 meters. That's roughly, I think, from here to the end of the room. So it's a big machine, but it's not unthinkably large. And it expands over Wendelstein 7X in the sense that we go to a different kind of superconductor, high temperature superconductors, which become superconducting already at temperatures of 80 or 90 Kelvin. But then we cool them down a little bit further to 10, 20 Kelvin, where the magnetic field that they can produce becomes still a lot higher. And so with this choice, we can go roughly a factor of 4 in fusion, in magnetic field strength. And because the fusion power depends on the magnetic field strength with the 4th power, now people can think 4 to the power of 4, it's 256. So basically, alpha would have an equivalent fusion power more than 200 times of that of W7X. And W7X has like 1%, so we get with this times 200 roughly to a factor of above 1. So the key deliverable of alpha is that we get to this Q greater than 1, which is like the first step towards a fusion power plant, which we want to demonstrate. And also we operate with deuterium and tritium, these 2 hydrogen isotopes that actually make up the fusion fuel that you need in the power plant. Tritium itself is radioactive with a half-life of 12 years roughly. And this introduces a lot of operational complexity, which we said like we cannot delay further. We need to put this into alpha already, learn how to use it, learn how to design a machine to do this kind of stuff. And then when we have alpha up and running, the step to Stellaris is still a significant one, but it's it's a lot easier than going directly from Wendelstein 7X to Stellaris, which some other companies suggest to do, but we think that's just presumptuous. And if we have alpha, we go towards Stellaris by introducing the so-called blanket, which is where we rebreed the tritium in the machine. Because tritium is not so much available on Earth, we need to recreate that from lithium within the process of that machine. And also we need to introduce remote maintenance. So there's a lot of robotics, PLC, and so on. So I think I'm in the right community for that here to actually get these whole remotely controlled operations figured out. If we now look at where we stand in terms of physics performance, it's all about big machines and using them with new machine generations to increase certain key properties, key deliverables, key numbers that allow us to judge how close are we to a fusion power plant. And one of them is the so-called triple product, which is the density times the ion temperature times the energy confinement time. And all of these 3 numbers multiplied together give you a single number that you can use to like ballpark judge how close you are to a fusion power plant. And all these little dots here in the background that you see, those are from tokamaks. And we have here with Wendelstein 7X the blue triangles. And you see that Wendelstein 7X really delivers towards the horizontal axis, which is the duration of this high performance phase. And we can see here that some of the Pareto optimal points here from the tokamak world have been acquired in JET, the Joint European Torus in UK, which features a plasma volume of 80 cubic meters and was operating in the so-called high confinement mode, where they kind of have a 2x improvement over the low confinement mode, which W7X was operating in for the same performance, and with roughly 1/3 of the plasma volume. So it's not only that the tokamaks and the stellarators are more or less on par with performance, it's like with these optimized stellarators, because you have these contorted coils which are numerically optimized, with the modern optimization tools, or like this optimization approach, which was already used for Wendelstein 7X, we're in the position now where we can design these machines to perform better than the tokamaks, which traditionally stole the show for the stellarators. And then with alpha, our machine, we say like the horizontal axis is what W7X has to deliver on, and we are focusing with alpha on the vertical axis, so we're aiming only for 10 seconds of plasma operation maximal at only deuterium, and with DT actually only at a couple of seconds, which is the time scale on which we need to prove that this works for this to be the relevant next step. And then with Stellaris, we go then again in the horizontal axis, but this means that we can demonstrate basically the technology already in alpha, and this little bit of vertical increase here simply comes from Stellaris being a bigger machine. It's not a different technology anymore, which means that a lot of the engineering learnings that we will acquire during building alpha will immediately carry over to Stellaris. Here's our roadmap, how we see this. And we start with W7X, which is the basis for all of this, which we say like in 2022, roughly it became clear that it was really performing very well, much nicer than we would have anticipated, and it broke several records in terms of this physics performance. Then in 2023, we spun out Proxima Fusion from IPP and directly built on Wendelstein 7X, so that's done. In 2024 and then published in 2025, we did work on a power plant concept, how based on this technology one could conceive a fusion power plant concept that as its most relevant feature was self-consistent. Because in the academic context, lots of people typically do like this deep dives in a certain topic, certain aspect of such a machine. But it doesn't necessarily mean that you can make a full power plant out of that, because obviously that entails more components than just, I don't know, how can you make a great coil set that achieves a beautiful magnetic field, but it's like so contorted that you cannot manufacture it. And with this Stellaris concept, we tackled really the whole breadth of it. And this was published in 2025. We're currently working on building the so-called Stellarator model coil, or SMC, which is a 3.5 meter magnet. So that's roughly the size of this screen plus a little bit, weighs, I don't know, 10 tons, I think. And it's going to be the demonstrator for this new high temperature superconductor magnet technology applied to stellarators. And you see it's a little bit stellarator-y. Other people in China and the US have already built coils of that scale which are planar, which is the thing that you need for tokamaks. So in principle, we know that's working. Then in the early 2030s, we hope we'll be able to take alpha into operation. And then I think, like optimistically speaking, within the 2030s, it is possible, it would be a hell of a ride, but I think it's possible to get the first Stellaris, first of a kind power plant thing into operation. In May 2026, we stand with 150 engineers, physicists, and operators in Proxima Fusion. We have offices in Munich, in Zurich, actually in Villingen at the Paul Scherrer Institute there, and in Oxford. So this is where this JET tokamak was operated until 2023. We have raised $230 million roughly of private and public financing. Plus we have a 450 million commitment from the Bavarian government and RWE towards financing Alpha as a facility in Bavaria. There's a couple of logos from our investors and render of Stellaris, which was this peer-reviewed publication in 2025 came out. This made quite a big wave when this came out. So the Dennis White, the head of the Fusion and Plasma Fusion Science Center at MIT, said this was the biggest development in fusion technology since the breakthrough in tokamaks a decade ago. And it's an open access paper. You can just download it. It's roughly 70 pages or so, so it's good bedtime reading. And a couple of quick facts here. It's a quasi-isodynamic stellarator based on the so-called SQUID configuration family that was developed at the Max Planck Institute for Plasma Physics. So it's a collaborative effort that we did together with the Research Institute and us and the KIT, the Karlsruhe Institute for Technology. It features these non-planar high-temperature superconducting magnets, uses microwave heating with 50 megawatts at 240 gigahertz, and pellet fueling has an island diverter, which is a certain way to reduce or get rid of the ash from the plasma. Very well developed in Variational 7X. And then we use sector splitting for remote maintenance. So if you think this machine is like a torus, and you view it from the top, it looks like a pizza that we just had. And then actually, just like the pizza slices, you cut it in 4 pieces, and these 4 pieces you can then move apart from each other. And thereby you gain access kind of to this whole cross-section here, which is very beneficial for doing maintenance of the components inside of this machine, which eventually will feature a little bit of wear from being bombarded with neutrons during the lifetime of this machine. And then a couple of quick facts here. In the end, it's maybe the last number is the most important one. We're aiming for a gigawatt scale power plant here. This is not some kind of small thing that you put on a truck, which I would myself say is a little bit unrealistic at the moment with our current fusion understanding. But this is really something which you could put in places of existing power plants, either being them traditional, I don't know, coal burning or gas burning power plants or fission power plants. Those nicely are already taken out of operation. So it's a little bit easier to motivate the utility companies to make these sites free. And with RWE, we are actually in the discussions already how to prepare the Gundremmingen nuclear fission power plant site near near Munich for the first fusion power plant. They are super eager to get engaged with this because this allows them to reuse this site with all its infrastructure instead of having to return it to total greenfield. This is a render of Alpha. A funny side note, maybe this rendering has been made completely with open source tools. So the CAD files here for this thing are built with Cut Query, which is a tool that allows you to programmatically construct step files or like CAD geometries in memory and then use them in CAD files. And I think the render itself is done in Blender. So we're very heavily leaning into the open source software community, and as I will show later, also a little bit contribute to it. And you see here again these like contorted coils. Then you have a lot of support structure in between them. In the middle you have the plasma, that is where the business goes on. A couple of human access ports where you can crawl into the machine, do some installations or repairs. And you see it's like barely big enough. It's a big machine, but I think it's roughly the size which is at the right compromise between being small enough that we can actually consider building this in this like couple of years that are there until early 30s, and like large enough and relevant enough that it actually pushes this whole field a step forward. We are very actively de-risking the assembly process of this machine. In Wallenstein 7X, the first coils, so these magnetic field coils, they arrived on site in 2004. But it took until 2015, so roughly 10 years later, for the machine to actually do its first plasma. In this whole 10 years, it was the job of Lutz Wegener, consultant to Proxima and ex-head of assembly of Wallenstein 7X, to figure out how to assemble this machine, how to really put it together. And the key challenge with that was that as the components kept coming in, because there was no like fully thought through CAD model plus assembly process that was validated with experiments and so on, excuse me, they needed to figure out a lot of this, how to put this thing together, how to align it, how to achieve the accuracies, the tolerances, like even just threading the coils over the plasma vessel with like 6 tons of coil on the crane and 5 millimeter clearance to put it over there, more or less semi-manually. This was a formidable challenge, and I have the biggest respect for the team who pulled this off at all. But of course, in Alpha, we cannot afford this long time scale. And so we are aiming for 3 years, and this is one of the key projects that I personally am involved in. And what we do is that we build Mars. Mars is the maintenance and assembly research sector, which is essentially one of these pizza slices of the machine, of Alpha, made in real hardware, not with the full fidelity, so we're not building actual superconducting coils, but we just cast them out of iron. So this is a nice job at the foundry. We have some nice the videos of that casting process on YouTube if you're interested. Quite impressive. I still remember this feeling when I was there in the casting hall, and then they put the metal in, and the styrofoam that they replaced with the molten metal was burning off, and that thunder from these flames still vibrated like you're in when this place is actually used as a discotheque. So it's a properly impressive process here. And the nice benefit of that is that we now have these components which we can precisely align and try out, like how is it really to align these heavy, big components. So this one is roughly 5 meters from side to side. The top coil weighs 8.5 tons, the bottom one 10.3. And like you can lean against it and nothing happens. Even when they are like a little bit wiggly on the floor, it's like you cannot put it, it's no chance. This is just super heavy stuff, and it necessitates that you really figure out your assembly processes, because when you're dealing with the actual coils, which will cost, I don't know, 5 to 10 million each, in assembling Alpha, this needs to work picture perfect. And so we're very actively leaning with the partner company here, DWE in Deggendorf, who has done similar stuff for Wallenstein 7X already, into de-risking this and really developing these processes. We embrace the principle of open science and closed engineering, deliberately, because fusion has this notion of like it's always 20 years away, which very happy to discuss it. I think it's a little bit of an ill-posed question, but like I think the approach for Proxima that has worked really well for us is that we ride this wave of credibility that has come out of this Max Planck Institute, which has done 60 years of publicly funded research with peer-reviewed papers, and there's like 1,000 scientists who've worked there and really established a solid ground of understanding on which we can now build our machines and our planning, of course. And so with the scientific aspect of that, which is nothing which you can patent anyway, or where it's more valuable to have this trusted and verified and like critically reviewed, even by our competitors, I would argue. There we are happy to open source that, to publish this kind of stuff. But the engineering bits of how to actually build such a machine, this is where the real value generation happens for us as a private company. And this is why this part is closed and will remain closed. And one open science project is this VMEC++ ideal MHD equilibrium solver. It sounds very complicated. In the end, what it gives you is the form, so the geometric shape, and the magnetic field of the plasma. And this is the basis for all further following performance predictions and analysis. And along with that, I said this 200 pages of LaTeX documentation, handwritten. This was all in the age of pre-AI ages. Then also this ConStellaration data set that I will say something a little bit later about, which consists of roughly 150,000 quasi-isodynamic stellarator designs that you can download yourself. I don't know, it's 500 gigabytes or so, including performance metrics, which we pose then as a challenge for people to apply their AI tools to and machine learning approaches and try to find better ways of designing these machines. And most recently also ray tracks, which is one of these microwave ray tracing tools that we use to model the heating of the plasma. And David Straub, one of our team members, is now a professor at the technical school in Munich, and he's even on his private blog posting about ray tracks still because he's supporting this further. And then I would also like to point out that we sponsor and present at a couple of conferences, for example, this open source software for fusion energy conference, where one of our team members is in the steering committee. And we have a couple of contributions to OpenMC, CutQuery, PANS, DugMC, SimSoft, by Proxima Fusion team members, and also sponsorship of these projects. So we try to really embrace the open source world in which from which we profit so much with all these tools. That's it for the first part of the talk. We have 2 more parts to go, so bear with me. Second one is now about VMEC++ itself, because this is a project that I started as part of my PhD. And in the announcement for this talk, I promised to give a little bit of a background story to that. So first of all, what problem does VMEC even solve? Or why is it a tool that's worth investing any effort in? It happens to occur that this is the central modeling tool in 2 essential but slightly different workflows when you want to work with stellarators. And one of them is the stellarator design workflow, and the other one is called equilibrium reconstruction. So the left part is basically how you want to build such a machine, how you want to design a stellarator. And the right one is if you have a stellarator, what the hell is going on inside of it? Because this plasma, it's like you can think of a bicycle tube, tire tube. Normally in a bicycle you have the mantle. But if you now, maybe you've played around with that yourself as well as I did, you take the rubber tube itself and you pump it up by itself. And then the shape that it takes is like a circular cross-section, but as you pump it out, it gets a little bit bigger in the radius itself, right? This is the hoop force is what pushes it out. And it's a little bit similar with the plasma in the magnetic field cage. So in the case of the bicycle tire, you have the inward pressure from the air that you pump into it. And you have the outward pressure, which is from the ambient, I don't know, 1025 millibar or so that we have here ambient. And the force balance between these 2, pressure force from the inside, the rubber force, and the outward pressure force, this is what gives you the shape of this tire. And in the plasma, it's basically the pressure from inside this plasma where you heat it up. So you have hot particles that are confined, so they want to move out. And from the outside, you have the magnetic field pressure, which pushes this stuff together. And so this pressure balance is what gives you the shape of the plasma, and this changes. So you need to somehow compute that. And in stellarator design, what you do is that you parameterize this pressure profile, so how the pressure changes within the plasma, and the coil current, so how much current do you run through the coils, as well as which shape do they have. And then you feed this into this simulation tool and you get out either metrics of physics performance that you then can iterate over for so-called scenario modeling. So how will this machine work over a time span of an experiment? And you can also calculate from the coil shapes and the plasma output some engineering metrics like how much heat load is going to be on a certain place of the internal of the wall and so on. And then you can iterate here over the engineering design. And in equilibrium reconstruction, you have the same modeling setup, except that now you have fixed coil shapes, because when you have the machine, you want to analyze it, the coils are not going to move. And then you calculate predictions for what the measurement instrument, the diagnostics, will measure. And you have some actual diagnostic measurements in your experiment, and then you look whether they match. And if they don't match, you iterate over the inputs to the simulation code. And you see that this is a rather similar workflow. So you have always this simulation code in the center, some parameterized input, and some metrics that you optimize for. And essentially what we do is that we then formalize this as a end-to-end function, and that we feed then to a multi-objective optimizer, scipy.optimize.whatever. It's really as simple as that. But that means that the simulator tool you need to call an awful number of times, because you need to really iterate over the simulation. And so this is why we decided, or I, during my PhD, when I was working on this on the equilibrium reconstruction at W7X, decided to invest a little bit of time into that. And like, so speaking a little bit more formally, VMEC gives you like these surfaces here, these shapes that you see here in the center, and the magnetic field of that. It solves a certain partial differential equation for that. Not going to go into the detailed analysis. It's just important to know that this is such a complicated geometry that you cannot simply solve this analytically. So you really need numerical tools to do this. And VMEC is the most well-established tool for this, also because since it was written in 1983 until I rewrote it in 2019, 2020, it was the single tool and the single implementation in Fortran, which was the world reference for stellarator research. So something needed to change. And this is how this computation looks like. So you start from a certain initial guess, and then as the force residual moving these shapes into force balance reduces here, you see that they move eventually into this nicely contorted shape. How does this came about? So again, the status quo for like 40 years or so in stellarator research was that VMEC was the central tool. There was only this one legacy implementation. There was virtually no documentation of the core numerical approach. There's a couple of research papers, but they didn't really, also like thinking about Dockling, one of these like totally unreadable, noisy PDF scans. So I'm very curious to try that out. And but the problem was that even there were these papers, they didn't really agree with what was actually implemented in the code, which is also not super helpful, obviously. And then the memory management was broken. So when you ran this code a million times, I don't know, 10, 20 times out of so, it would randomly segfault because it took like this one weird approach, or one weird code path, which then led to a problem. Because like in the context of running this code within an optimization toolchain, you're essentially fuzzing it with its input, and nobody had fuzzed VMEC in this. So it was all, usually the workflow was like somebody sent someone an email with the input profiles, and then the VMEC expert at the institute was running the code himself, and then was emailing back the results, and then they were discussing with the email and so on. Naja, we have progressed since then. And the like more abstract level reasoning, I think in the end was that with Vanillage 7X, we saw that this machine was really working well. But we said like, it seems a little bit bonkers to have this billion-dollar class of machines that we want to build here. Vanillage 7X cost 1.4 billion euros and took this like 10 years to build. So it's a massive investment that you make. And this engineering design for this machine was based on this black box Fortran code from the 80s that nobody understood. And so we thought about, okay, it works well, but we want to build the next billion-dollar class machine. So are we really going to do that based on this black box that nobody understands? No. So the journey. I started 2018 with my PhD thesis, and then for the first year or so, I listened to what my supervisors told me. And then I thought, hey, I really need VMEC. And I don't want to do it with this legacy Fortran implementation. So I suggested openly to do something about it and analyze it, rewrite it, I don't know, clean it up. I had to survive a lot of pushback there, obviously, because they were worried that this would take a little bit longer. And guess what? It took, in the end, 4 years. But yeah, in the end, they said the only thing you need to do is listen to our feedback. And then in the end, it's your project. You're the project manager of your PhD project. If you mess it up, you just don't have a PhD. That's okay. I was fine with that. So I put the PhD topic aside and like fully focus on this rewrite of VMEC. I defined a couple of reference cases, dumped reference data from the Fortran implementation. If people are interested about the details, I have a couple of backup slides, or I show you actually on the laptop how this worked. And then used that for a one-to-one, like literally like line by line, by hand, again, pre-AI times, copying what was done in the Fortran implementation into Java with the Eclipse IDE, because I liked it, and this was where I was at home. And then, well, questionable life choices, but here we go. And then once that was working and I had full set of integration tests that achieved the same numerical results as the Fortran implementation for the relevant set of input files, I sat back a little bit, wrote a lot of this documentation, and in the process always implemented then a clean version of how I understood the numerics to work in Python. And then my PhD contract ended, because clearly I was not working on my PhD topic again. But the thing is, this project had matured far enough, and also we saw really with this Wendelstein 7x results that something was happening in the case of fusion. And also, third part, in 2018, a certain American spin-out from a certain American university raised $1.8 billion based on building their version of this demonstrator coil for building their version of their tokamak power plant. So we said, okay, something is happening in fusion. We need to somehow get now to do something based on Wendelstein 7x, because if we don't do it, somebody else is going to do that, and what would that be? And so we co-founded, or I together with a couple of friends co-founded Proxima Fusion. And then we did the from scratch proper high performance implementation of this VMEC code in C++. And this is also the one that's now open sourced. I have to give a huge shout out to Enrico, Veronica, and Philip, who were 3 early team members who helped a lot, in particular Enrico with the performance optimization and rigorous integration tests, what Veronica mostly worked on, the verification and validation against the Fortran implementation, to the point that we decided to open source release it in end of 24. I think it actually became online in 2025. And it's in daily use at Proxima Fusion since 2024. It's our core simulator for these plasma shapes. And yeah, this numerics of VMEC++, which is this document that was released along the side, it's now also available also on archive. And we have a growing example collection very nicely also now, with more and more contributions from the community, where just somebody opens an issue and here's how you visualize the magnetic field. And I'm like, nice. VMEC++ is a modern Python-friendly VMEC implementation. We still do a lot of, or we do a lot of our analysis and modeling in Python. It's easy to install, pip install VMEC++. It's all supported mostly on Linux and Mac OS. It has some direct integration on C++ via Bazel and CMake. It's downloaded mostly in the United States, second mostly in China, and MIT license, so you can do whatever you like with it. The API is a single method, single static function call. And here's a couple of examples. So in particular, this middle one is a self-contained VMEC run, something that this Fortran code would do. And it, you can read the details later. It's well documented and tested. We have a bunch of CIs set up and the documentation. It's validated against the Fortran reference. So we have here some demo plots where the blue and the red are overlaying here picture perfect with 10 to the minus 12 relative errors. So we say like this is close enough that it's just like how the compiler optimizes certain ordering of operations differently, and then okay, you get a little bit of numerical noise, but like for all practical purposes, it's the same code. And this is also something that I decided with VMEC. I don't want to dive into writing a new code and actually having to understand the theoretical physics that go on there. I'm just an experimental physicist who has this code. We know it works. I'm going to port it to a modern code base, and then we can think about the physics variations of that, which is something that we're getting into these days. And let's see also how this enabled us to accelerate this execution of the code a little bit. So because I mentioned this original implementation was more or less the same since the 1980s. Back in the day, it was written for the Cray 1, which is a vector supercomputer. And that means all the operations were operations on a single 1D scalar array, which is like not exactly ideal for modern CPU architectures. And so by reformulating the ordering of the operations a little bit, we were able to help the compilers auto-vectorize a lot of these operations, and that gave us a nice speed up. A gray, always the old one, this turquoise here, the new one. And something else that was the key motivation for me to embark on this project is that since it's an iterative code, which needs like 5,000 iterations, and then you do a little bit of finite difference step, you only need to do the last 100 iterations are a little bit different, and all the like previous iterations are the same, more or less. And that means that when you can save the internal state of that code and like hot restart it from that converged state when you do the perturbation, you can save 90% of the time. And obviously this involves a little bit of memory management, and you need to get quite detailed into the innards of this code. And this was then also easy with VMEC++. I gave up after 2 months of trying to do that in the Fortran code base because I simply couldn't figure it out. And here you see basically then the runtime reductions from the normal every run from scratch implementation of an actual optimization problem down to like 1/10 of that if you use this hot restart feature. Okay, then I come to the last topic, this ConStellaration challenge. ConStellaration is basically what you see here on the right. It's like every little thing here is a stellarator design. It's 160,000 in total of this plasma boundary, so like the shape of the outermost surface of this plasma, the actual equilibrium calculation and the metrics. They are available on this Hugging Face data set here. There's 3 optimization benchmarks with the tools and the baseline results. And we have a public leaderboard on the challenge with Hugging Face where people are submitting their results and competing for fame, I think, mostly. And we also have a paper on arXiv that goes a little bit into more of the details of this challenge. Why do we need this even? With stellarator design, you always have to trade off between certain objectives. This is also what I mentioned earlier with the Stellaris design, where we really leaned into this consistency and like being okay at everything instead of super good at something and very bad at something else. Maybe the easiest to comprehend is like this bottom 2, where you have the dark red, which is the economic target. So like this is very cheap and this is very expensive. And then the orange bit here is the physics target. So this has very nice physics and this has not so great physics. And you obviously can see that this is a much simpler design, but it just doesn't work so well. And this one is where the physicists were really happy with, but it's like horrible to build when you look at these coils. And so in this space, you need to choose where you want to put your eggs. And this is what we try to trigger with this ConStellaration challenge. And then how does this work in practice? We have here this plasma boundary, which contains most of the information that we need for this calculation. It's a bunch of Fourier coefficients. Here you see like the values of those. Then we put this into VMEC++, which computes the full magnetic field inside the plasma, also with these inner flux surfaces, which is like how the plasma is internally organized in this model. And then we compute a bunch of metrics, which are just scalars or 1D arrays or so of certain numbers. And some of them you want to be high, some of them you want to be low. Then you feed this into an optimizer, and then the optimizer suggests a new candidate. And then you just iterate this loop until you're below a certain convergence target. The optimization benchmarks that we have published are 3 of increasing complexity. So first one is the simple geometric one, where you just want to have certain metrics below a given threshold. Second one is a simple to build quasi-isodynamic stellarator, where we have this L grad B metric, which is a metric that is related to how wiggly these coils need to be. And the third one is the MHD stable quasi-isodynamic multi-objective problem, which is the minimum viable subset of metrics that are actually relevant for the stuff that we do during our daily optimization work. If you're curious for more, I think the first thing is ask Roland Busch, because again, he's been at our lab and he knows, actually he did his PhD on high temperature superconductors. So it's really nicely closes the loop. And otherwise, check out our code. Here we have our GitHub project, and then there's my email address and also the one of Santiago for this ConStellaration challenge. And if you actually consider contributing to this project, we also have a link here to our page of open positions. Thank you.
I have a question. Or my question have been answered, so we know which tool we can use to design one. But I guess nobody here has the money to build one.
Siemens certainly has the money to build such a machine.
You're right. Yeah.
That would actually be part of my question. So can you shed a bit of light on if you have ideas already how to operate these things control-wise? Now, we are control engineers, so we are interested, okay, what problems you need to solve at this level, what controllers you need, what speed you need, and things like this. Are there ideas for that? Or there must be from the operation of W7X, I guess.
The thing is, that's a little bit of an unfortunate message for you, I think. Stellarators are just so stable that you don't need so much control. But, there's always a but. You do need, of course, certain control systems for a stellarator, and that is, I don't have a picture for that now, but if you look at these time trace plots where you like go over the time and then you have multiple quantities, you always see that, for example, the plasma density, typically it has a set point and then it wiggles a little bit around it. And this is because the PID controller for that density feedback is not really tuned properly, as it is when you just have spent 10 years building the machine and then you want to operate it. But like, yeah, there's a couple of control mechanisms on the higher level of physics around this machine that you keep it at a certain operating point. The response times for that are on the order of like fastest is maybe a millisecond down to 100 milliseconds. So easy to do, I think. We could go to S5 maybe, who knows. And then other than that, I mean, there's really no fast, the next interesting bit is then when you have done such an experiment, how quickly can you download the data from the data acquisition units, do some preliminary physics analysis and use that to inform the machine operators what they want to change for the next experiment. Because at least in Wendelstein 7X, it's always run for, I don't know, 10 to 30 seconds. And then you have 5 to 10 minutes of a break where people try to understand what the hell just happened and tune a couple of knobs and maybe we need to up the density a little bit and then da-da-da-da-da. And yeah, this would benefit a lot from automation also. And we're not there yet with what is possible, even at Wendelstein 7X, not yet. But there's a lot of potential. Other questions?
Yeah, thank you. I actually have two questions. So my first one, you mentioned while assembling all of that, you run into shortages of materials sometimes. Like, do you see in the future when it will work and scale to multiple sites that in the world we will have a shortage of something you need?
Maybe I misspoke. Like, the problem is not that we don't have the material coming in. The problem is we have so many components coming in at the same time, and we need to be able to assemble them together quickly enough that they don't pile up in the logistics hall, and then you don't find the one screw that is just at the bottom of the pile. So even if we go to multiple stellarators, I think there's a couple of things which are not at the production scale yet as we would need it. For example, this high strength stainless steel that we need for the magnet coils. But this is nothing that could not be ramped up in the proper industry sector when the demand is there, because actually like there's billions or tens of billions of euros, dollars, whatever, flowing into this industry and the demand being there. At the moment, the demand is not there yet, and therefore the capability is not there yet.
Thank you. And the second one is a little bit more personal. Did you ever think when assembling to put 4 robotic arms on your back?
It's a nice idea. I haven't figured out the design of this neural link yet. So that's why we still have to revert to good old cranes and hooks and all this kind of stuff. But nice idea.
Perfect. Thank you very much, Jonathan, for those insights.